Thank you very much, Vitali, for the very kind introduction, and thanks all of you for inviting me as a trained computer scientist. So I feel honored. This is actually a talk about computing Bayes Nash equilibria in auction games, and it's joint work with a number of my PhD students. So the ones who are still on board are Max Fichtl, Stefan Heidekrüger, Nils Kohring, and Matthias Oberlechner. I thought before I jump into the agenda, I want to motivate this a little bit with something that you're all very familiar with something that you all know, which is essentially the Bayes Nash equilibrium strategy for the first price seal bid auction. And this is really taken from Krishna here. But just to set the stage, this goes back to essentially William Bichler, who showed us how to find a Nash equilibrium in a Bayesian game with continuous action and type spaces, like a standard first price seal bid auction. And to cut it short, what he did, he started with the expected utility, and beta here is always the bid function. P is the bid price in this first price seal bid auction. We here have a standard quasi-linear utility function. And then, you take the first order condition, assume symmetry, and then you end up in an ordinary differential equation, and you get an analytical solution, a closed form solution, which is very nice, right? And this has obviously, been a landmark paper, been a cornerstone for his Nobel Prize, and so on and so forth, right? And when you talk about single object auctions, I think we have a very complete and very nice framework to think about auctions and a way to model it. A couple of years ago, we were tasked to think about multi-object auctions, and that was a collaboration with an industry partner, and that was a project about procurement auctions, so-called split award auctions. And I want to spend a bit of time on this because I will revisit these types of auctions later when we talk about experimental results, and they have some nice equilibria. So we actually, as you will see, we will find multiple pure equilibria in this game, right? So the setup is also a first price seal bid auction, and we have two lots or shares. So essentially, we have here 100% share or a 50% share. So essentially the buyer here, so we are in a reverse setting, asks the suppliers to submit bids, and these submits could be on the entire contract or on a 50% share only, right? And this is also why it's called a split award auction, an ex post split award auction. And we started looking into existing literature, and as you probably all know, we really don't have a nice closed form solution for first price seal bids, combinatorial auctions in general, right? So, we started digging into it, and you have a lot of degrees of freedom. So we added more structure to the problem, right, in order to finally derive some equilibria. So, and we stick to standard environment. Like we looked at independent private values here. We assumed that we know the exact lower and upper bounds of the prior distribution. And most importantly, we assumed a parameter C. So, which is maybe not totally unreasonable. This parameter C describes the efficiency of in this market. Essentially, if you have economies of scale or diseconomies of scale, right? So if you have a parameter C that is rather small, say as described in here, then you would have diseconomies of scale. As an example, you might have a parameter C of 0.3, and the cost for producing 100% of the contract is, say, 100. Then the cost for producing 50% is your cost raw times C. So this would be 30 then, right? And this essentially is assumed to be publicly known among the bidders, right? So this is the setup. And assuming that this publicly known parameter essentially did the trick then, right? And we could then find equilibria in this game, pure Bayes Nash equilibria. One is the winner takes all equilibrium, where actually both bidders just compete for the 100% share, which is inefficient if you're in diseconomies of scale or in this dual source efficiency, right? So if you have strong diseconomies of scale, you would want to award the 50% of the contract to the most competitive bidders, right? And we call that the sigma or split equilibrium, right? So, and we could identify those two equilibria. The sigma equilibrium is the efficient one. The winner takes all equilibrium is not, right? So took a while, and maybe as a specific setting, you might want to envision an environment where you have only two suppliers and these two shares, right? This is a bit of a specific case that goes back to a paper by Anton and Yao many years ago, who already analyzed that, not the general case. But it's interesting because it's a pooling equilibrium. So independent of the cost draw of the bidders, they would pool, they would bid the highest possible bid, which is V upper bar, so the highest cost draw possible on the 50% share. And again, this is independent of their cost draw. And they cannot just bid infinity then on the 100% share, because that might set incentives for bidders to deviate to the 100% share, right? So they need to bid just competitive enough on the 100% share as well, right? So this is just a bit of a story, and why I'm telling you all this. We are gonna revisit this a little later when we talk about experimental results. But it's an interesting environment because we know two pure base Nash equilibria. There might as well be mixed Nash equilibria. We don't know, right? So another reason why I'm telling you is this essentially kicked off this project because I found the whole exercise a bit frustrating in a way, in the sense that we did have to make a number of assumptions, right? So we had to assume this publicly known parameter C, V upper and V lower bar are public knowledge to all of those bidders. We had to stick to independent private values and risk neutrality, and so on and so forth. And comparative statics turned out to be super hard, right? So, and it still ended up being a 4 or 5 page proof. And it took quite some time, maybe because we were so unexperienced, that might be a reason, but it's in general, I think these types of analysis are time consuming, right? So, and that's kind of the motivation essentially for what we did. So when you think about auction theory and the equilibria that we know, again, by and large, I think single object auctions, in particular in the independent private values model, are really well understood, right? When we look at multi-object auctions, there are specific environments, we will talk about some in this talk, where we do know the base Nash equilibrium, or at least we can characterize it, but in many we just don't know, right? And in particular, when you add things like type interdependencies, asymmetries, multiple objects, you often end up in a system of partial differential equations, which, you know, we don't have an exact solution theory for in general, right? So what do we know about existence at all, right? So there is some general work by Milgrom and Weber. So this was one of the early papers that looked into these types of equilibria, and they actually came up with distributional strategies, which is the mixed extension of a pure base Nash equilibria here. And that's something we will get back to a little later. Then there is this famous paper by Susan Athey on the single crossing property, which kind of lays out properties for which we can expect pure base Nash equilibria to exist. Jackson and Swinkles is a landmark paper because it kind of really broadens the scope of environments where we know base Nash equilibria exist. And the literature goes up until 2018 and probably even later, right? So this is what we know about existence, but it's still much more restricted than the very general result by Nash from 51, right? What concerns us in computer science even more is computation. So you might all know, so after the existence result by Nash, it took almost 60 years until complexity was understood. So in Daskalakis, Goldberg, and Papadimitriou published this amazing paper showing that in general, in finite games, computing Nash equilibria is PPAD hard, right? We know much less in these Bayesian games with continuous type and action spaces. So there is one interesting paper by Kai and Papadimitriou, and they showed for a specific setting only, where you have a number of parallel victory auctions, and bidders have very simple utility functions in the sense, so say one environment that they analyze is all of the bidders have additive valuations except one who has a unit demand valuation, right? And they showed that already for this setting, the exact computation is PP hard, which is way beyond the polynomial hierarchy. So even if you don't haven't looked into complexity theory, so this is totally intractable. So this is way beyond the maybe standard NP hard problems that you might have heard about, right? And that maybe explains to some extent why we don't have a lot of literature on computing Bayes Nash equilibria in these games. So there are some sections in a paper by Bajari, Susan Athey spent a bit of time, but this is kind of far away from an algorithmic treatment. There is nice work by Bossert and Seuken and his colleagues from 2020, but it's also computationally very demanding. And it raises questions, first of all, what is the value of an equilibrium solution concept that is totally intractable, right? So how can you assume that bidders would play an equilibrium if it's so super hard to compute, right? And the second question maybe is, wouldn't it be nice if we had numerical techniques to approximate these equilibria, right? Maybe this is possible, and then we could maybe, get predictions for the type of equilibria that we can expect in a particular game, right? And maybe this is even possible without setting up the system of partial differential equations. And that's essentially what we're after in this project. All right. So we started out looking into equilibrium computation. And
sorry, Martin.
Yeah.
I have a question.
Sure.
Well, it's maybe more of a comment. I don't know, but basically, you are saying that we spend 60 years looking at something that has no relevance because we cannot compute it.
No, that's not what I'm saying. I'm saying if it is indeed so that it's totally intractable, then maybe the predictive accuracy cannot be expected to be very high. But let me not go ahead on myself, but I'm bringing some positive news here, right? I think we can compute, at least approximate Bayes Nash equilibria for a large variety of games. And that's the core of this paper, actually. All right. But there is obviously research on equilibrium computation, and some of the literature goes back quite a bit. You might all have come across fictitious play. And then people looked at best response dynamics, and that goes back to the early 50s, really. In the early 2000s, computer scientists came up with gradient dynamics. So this is all for finite complete information games, I have to say. But here you aim for the mixed equilibria, right? And you essentially take a step in the direction of the gradient in each iteration of the algorithm. And I'm talking a little bit more about that in a minute. And online gradient ascent or gradient ascent, simultaneous gradient ascent could be covered under this umbrella. And there is a whole class of such gradient dynamics that are covered by the term no regret online algorithms. They are known to converge to coarse correlated equilibrium, right? Unfortunately, there are apparently games that where the equilibria or the states that such dynamics converge to are even dominated strategies, right? So this is not very telling. So what you really would want to have is an algorithm that converges to a Nash equilibrium, ideally, right? So in these Bayesian games that we are looking into, this is actually very hard. So it is well known that standard finite games can be written down as variational inequalities. If we are in our continuous type and continuous action games, these are actually infinite dimensional variational inequalities. And we really, again, don't have an exact solution theory for those, right? So if you ask yourself, well, maybe we could implement gradient dynamics, but how would we do that if we have continuous type and action space? So that's the next question I try to address, right? And then the second question that I try to address is, say, if we can do that, if we can implement gradient dynamics on such auction games with continuous type and action space, well, when can we expect those gradient dynamics really to converge to the Nash equilibrium? And these are the driving questions for the main part of this talk. All right. So let me talk a little bit about simultaneous gradient ascent for finite games. So what we take it as an input here is a complete information game with some set of bidders. A is a discrete set of actions or bits, say, and U are the utility functions as usual. And we also take some step size eta. So the algorithm in general is very simple. So at the outset, in each round, bidders submit a bit, bit. T is the very round that we are in. Then we observe the utility gradient. And I'll be talking a little later on how exactly we get the gradient of the utility. But if we have this utility gradient, we essentially just take a step in the direction of the utility gradient. So it's nothing else than gradient ascent that is being implemented here. And sometimes you might be outside the feasible region for whatever reason, might come up with a negative bit, then you project onto the feasible region. So it's projected gradient ascent. That's kind of what is described here in this pseudocode. Okay. Very simple algorithm, very widely used in convex optimization. So first observation is we're talking here about complete information games. That might not be such a big deal because if you look at the ex ante state of the game, you can interpret this as a complete information game, right? However, if you're in the ex ante state, then you have an infinite dimensional type and action space, right? So you don't submit a particular bit as is described here. You submit a bit function in the ex ante space, right? So what we do in NPGA, and that's the technique I'm going to introduce in a minute. So this stands for neural pseudo gradient ascent, is we replace this bit function by a neural network, right? And this neural network is pi, and it takes as an input vi, the valuations, and theta here are the weights and biases of the neural networks. So the parameters of the neural networks. And the nice thing about this is we now transform this game back into a finite dimensional game because we only have a finite number of these parameters, right? So essentially, we replace the original game by a proxy game, which is played in the finite dimensional parameter space of the neural networks. And the learning is essentially that agents or neural networks adapt their behavior by taking a step along the gradient in the parameter space of these neural networks. Right, so that's the general idea.
If it, one clarification question, the incomplete information game is infinite dimensional because you assume a continuous valuation grid, right?
Exactly.
Yeah. Okay.
Mm-hmm. Yeah. So please ask questions if there is anything unclear. Right. So let me talk a little bit about the neural networks that we are using. And you must have lived under a rock if you didn't come across standard neural networks, but this is essentially what we're using. We use standard feed-forwards multi-layer networks. So just the bare essentials, we have some inputs xi, we have weights and biases here, and these are fed into an activation function, and this could be a simple sigmoid activation function. For example, if you have a one neural network, it would be much like a logistic regression essentially, and it spits out a number, right? And these activation functions could be the sigmoid functions or reload functions, which is what you see on the top right. In the forward pass, we feed in the data, the training data, or if we want to classify something, for example, a particular data set that where we want to do a prediction. And then the input is multiplied by the weights and biases in the various layers, and then it determines the output, right? And usually you evaluate the output then by a loss function, right? And for example, if you do image recognition and you want to detect whether something is a cat or a dog on an image, you get a right or wrong. And depending, and you could have, for example, some quadratic function that determines your loss, right? So we replace this loss function by the utility function, right? So you could be arbitrarily creative with the utility function, but say the utility would essentially be your allocation xi times the valuation minus bi, and you could, as in this example here, add a term that makes it some risk-averse utility function, right? Or you could be, you could replace this by anything you'd like. And you might now ask, well, where does the training data come from? When we train these neural networks, well, it comes from self-play. So essentially what we're doing is neural networks with self-play. So the neural networks play against each other many, many times. So how does the learning now work? Let me start with standard learning in these feed-forward neural networks. And standard learning is done via backpropagation, which is essentially gradient ascent in this parameter space. Right. So an epoch in this training is one pass through the training data set. So you go through all of these instances in the training data set, and then you do slight adjustments via backpropagation, which is using the chain rule from calculus, and then adapts the weights a nudge in the direction of the gradient. This would be super expensive if you did this really for each instance. So there are a lot of very effective optimizers. Things like stochastic gradient ascent is used commonly, ADAM, ADAGRAD, and whatnot, right? So people have been very creative in coming up with more and more effective ways to optimize these neural networks. And what is important now is we have these universal approximation theorems, right? So the first one, there are different versions, I have to say, but I think the first one really goes back to Kohring, who happened to be one of my teachers in Vienna, and he shows that these multi-layer neural networks can represent arbitrary nonlinear functions, right? Which is nice. So you could now say, well, we do self-play with neural networks, but the standard trick, standard gradient ascent, unfortunately doesn't work, right? So that's the first problem we bumped into. Why is that? Well, actually, our utility function is discontinuous. So the plot here might give you an idea. So this is a plot that shows essentially the utility, the ex post utility of a particular bidder if you played a particular auction, and B sub minus I is the highest bid of your opponent, right? And if you bid below this threshold, well, then the gradient is always null, right? Because you don't win. If you bid higher than this threshold, the gradient is negative, right? Because the higher you bid, the less payoff you have. So essentially, at the end of the day, and that's what you can actually show empirically, all your agents will be a bit null, right? So that's not super useful. And it took us a while to figure out what the problem is. But the point is there are workarounds, right? And one of the workarounds that we used here is evolutionary strategies. So this is a technique, it's a general meta heuristic, but a technique that we can use here to determine pseudo gradients, right? This has been done in other work that is essentially about, scaling neural networks, so totally different application. But the way to think about it is really a smoothing technique, right? So you want to smoothen this discontinuous step here. Right? And with that background, I can now guide you through the pseudocode of neural pseudo gradient ascent.
Can I ask a question first?
Sure.
So I thought that you approximate the bidding function with the neural network.
Yes.
So do you then compute expected utilities? I mean, they would be smooth.
Right. We need expected utilities. So this is actually what is in the pseudocode here.
Okay.
Right. So maybe let me go through the pseudocode and see if that answers your question, and then we can get back. All right. So what is the input? We have a set of agents. These are our neural networks. We have an initial policy, and this could be random. So this is a random parameterization of the neural networks. What we actually do right now is we pre-train the neural networks. We pre-train them to be truthful, right? First of all, this has the advantage that the different runs in experiments are much more comparable. But second, it also showed that we converge a little faster. Then we have some initial set of parameters of the neural networks. We have a number of parameters for the evolutionary strategies in a learning rate eta in a particular batch size. And the batch size, I'll get to that in a minute, is very large. So this might be 2 to the power of 18. So say 260,000 batches of or instances of valuations that we draw. And that's actually the first step in the first iteration here. And you will see the overall outline is very similar to the short pseudocode that I was showing you before. We draw a batch of valuations, so many, and then we compute a joint utility, which is kind of the average utility with the current set of weights and biases for the neural networks, right? And then for each agent, we draw a set of perturbations of these parameters. So these perturbations are essentially nothing but we add Gaussian noise on the parameters, right? And each of these perturbations gives us a new instance of a neural network. And then we evaluate the fitness, which is again also the average utility for all the instances that we've drawn at the beginning, right? And then we can compute the fitness weighted perturbation noise. So this is what you see down here. And that gives us actually a pseudo gradient. And here we draw on Salimans, an earlier paper, who showed how to do that in particular, right? So it kind of gives us a pseudo gradient for the expected utility, right? And well, then we multiply this pseudo gradient times eta, which is the step width, which is what you typically do in gradient ascent, and we add this to the last set of weights and biases of the neural network, and that gives us our new neural network or our new bit function. All right. Bernhard, did that answer your question?
Yes. How do you introduce asymmetries in the evaluations?
I'll get to asymmetries a little later. So currently we focus on symmetric games, but I'll comment on asymmetries in a bit.
And in each step you optimize the bidding function for one agent, that means for all.
If we have symmetric games, so if you take Krishna, all chapters except one, I think, are on symmetric games, meaning symmetric priors with symmetric equilibrium bit functions, which is kind of the standard assumption. We obviously also looked into asymmetries, and I'll get to that in a minute. The proof we have for this particular method is for symmetric games, which makes it a little easier because we essentially have to train only one network. But if you have asymmetries, you can train multiple, right?
Yes, that was my question. So you don't have two networks and then you average them or whatever, but you train one and you assume that everyone's playing this one.
In a symmetric model, there is simply no need to train more than one. Mm-hmm.
But that would imply that you cannot find asymmetric equilibria.
Bear with me.
Okay.
So I'll get back to that. All right. So the long story short, we have convergence results. So we can prove convergence for symmetric games, and I'll show you why. We have empirical evidence that this method actually converges also for asymmetric games, and I'll show you some empirical results. And then towards the end, if we have time, I'll show you another method that we've been working on just recently, that where we can show that if we converge, then it's also a Nash equilibrium, right? And we do converge in most of the asymmetric cases that we've seen, right? But you know, this is the long story short. I'll get to these points. Right. So, but let's talk a little bit about convergence now, right? So what is known from the literature is that gradient dynamics converge also to these coarse correlated equilibria also in finite type continuous action Bayesian games. We are actually in this framework because remember, due to the fact that we use these neural networks, at least this proxy game where we play in the parameter space of the neural network is a finite game, right? So the question that remains is when do we actually converge to Nash equilibria, not just to coarse correlated equilibria? And we really looked at the literature quite intensively, and there is quite some activity in that field. But we realized after a while that these symmetric games have one nice property because they are essentially potential games. Right. So let me remind you about potential games, which you're probably well aware of. But an exact potential game would be one where you have some utility function and some strategy theta I, and you compare the expected utility of theta I to the utility of theta I prime, and you have for all the agents, and you have a potential function that gives you the same difference, right? So this would be an exact potential function. So if in a purely symmetric game, it's almost trivial because you only have one function, right? One utility function, which is at the same time your potential function, right? So here, this helps us a lot to get to the main theorem in this paper that says in any symmetric and smooth auction game, and this is a bit abbreviated here, symmetric MPGA with appropriate gradient update step sizes, we have to make a few standard assumptions here on the algorithm, converges to local ex ante kappa-Bayes Nash equilibria, right? So I want to mention locality here, although you will see in a minute when we talk about the experiments, we always found the global Nash equilibrium, right? And I should also get back to Bernhard's comment. So we also converged in the asymmetric game. So there is apparently some underlying truth that we haven't discovered yet that also makes us converge in asymmetric games. So here is a bit of an overview of the types of experiments we ran. We looked into single item auctions, multi-unit auctions, and combinatorial auctions. For the single item auctions, we looked primarily into first price Hilbert auctions. VCG is kind of trivial, and we looked into symmetric games and asymmetric games, risk averse, risk neutral, and different types of priors like Gaussian and uniform priors. For the multi-unit auctions, we looked at different payment functions, discriminatory and uniform. And then we also looked at combinatorial auctions, in particular, the well-known local global model. So for some of you, this is very well known. So this is kind of a standard model that's often being used in the literature on spectrum auctions. You essentially have two items, three bidders, two local bidders who are only interested in one item, and a global bidder who is only interested in the package, right? And this LLG model is very well studied, which is a big advantage. And in particular, there is work by Ausubel and Baranov, and they, they provided analytical solutions for different types of payment functions. So even if you're not in spectrum auctions or core selecting auctions, there are different types of payment functions where you choose points in the core, and there are different ways on how to do this. And in this paper, they actually went through a variety of these payment functions with independent private valuations and with correlated valuations, and provided the Bayes-Nash equilibrium strategy. And then we also looked at a very large setting with 6 bidders and 8 items. And in contrast to the LLG model, in this environment, bidders are multi-minded, so they're interested in more than one package, which makes it interesting. For this, for example, we don't know an analytical solution. And we also looked at the split award auction that I was telling you at the beginning, right? Because this is interesting, we know we have 2 equilibria, and we were interested in what would happen. So we primarily looked at environments where we have an analytical solution, simply because this is an unambiguous baseline to compare against, right? The ones with an asterisk here are the ones where we don't have a Bayes-Nash equilibrium strategy. For those, we can compute an estimator for the utility loss, right? But just comparing against many other bits, so to say. All right, so here are a few results. So let's start with the standards, symmetric single item auctions. We looked at uniform priors, risk neutral bidders, or risk averse bidders, or Gaussian priors, and different numbers of bidders here. And maybe the column to look at is the relative utility loss. So this is really measured if you take the strategy that comes out of NPGA, and you have this strategy played against other competitors who play their analytical Bayes-Nash equilibrium strategy, how much worse off would you be, right? And that's essentially what you see here. So the utility loss is super small. So the utility would be in the order of 0.2, 0.3. So the loss from deviating is typically very, very small. And with a small variance here, as you can see, you might now ask how long does it take? How many training rounds do you need? With uniform price, it's fairly fast. So within 7 minutes or a few minutes, we got a result and we converged. With Gaussian price, it just took longer because you need to get precise in the tails, right? So up to 1.5 hours, kind of. Since you were asking, so this is now a picture of the Bayes-Nash equilibrium strategies for asymmetric price. So there is a well-known paper by Plum from '92. And we have a strong and a weak bidder, and the solid line is the analytical result. The dotted line mimics the outcome of NPGA. Right? So this is kind of the type of results you get. Of course, with NPGA, you would also get a continuous line, so the dots are just here to mark a difference to the analytical result.
Do you fix the lower bound to the lowest possible valuation, or do you determine that in equilibrium as well?
Well, the valuations are drawn in each round of the auction that we play, right? From
but what I mean of the bids, do you say that 5 is the lowest bid in this?
No, so the bids have to be positive in this specific implementation, but not more than that. So this is maybe the more interesting setting again, the local global model now with independent private values. And here you have these different payment rules. Those of you who are familiar with combinatorial auctions might know about those. Let me not get into the details. They lead to different equilibrium strategies. Here again, calligraphic L is the utility loss. You see sometimes the loss is negative. So this means this is just numerically instabilities here. It's really super small. We also provide the root mean squared error here to compare the analytical Bayes-Nash equilibrium to the one that we find with NPGA, and it's also fairly small. And then here we also look at the first price heel bid auction where we use our estimator for the utility loss, right? And with uniform price, the computation is actually fairly fast. It's a few minutes only. This is just a plot. So the green line here would be the equilibrium strategy of the local bidder. Again, the solid line is the analytical solution, the dotted line NPGA. And you see that this we are on spot, so to say. And the strategy for the global bidder is easy because it's a dominant strategy. These are now the results for these LLG models with correlation. Also here, fairly low utility loss, low root mean squared error. Right. This is now interesting. Maybe this is a different way to depict the results. Namely, we are looking at the local or the large LLG model, so to say, with 6 bidders, 2 global and 4 local bidders. And this just plots the utility when it converges and the utility loss, which is the dashed line down here. So you see, so after 300 rounds, we kind of converge in terms of utility loss, right? So again, also here, we don't have an analytical solution to compare against, but we can, play against many other strategies. So this is actually computationally very expensive in a way when you want to get a good estimator. But the utility loss was very small here. And last but not least, and that was the reason why I was telling you about these split award auctions at the beginning. These are the results for the split award auction. So that now needs a bit more explanation. I was telling you about this specific scenario where we have 2 bidders and 2 lots. So the 50% lot or share and the 100% share. And the gray shaded area now in here and in here, this is the range in which we can find pure Bayes-Nash equilibrium. So there is a whole range, right? And the payoff, so I was telling you in the 2 bidder example, we have a pooling strategy. So independent of the cost draw, you would bid the very same bid, namely the highest possible cost draw. That would be your bid. So essentially, this is a form of tacit collusion in a way, where these two bidders collude on the 50% share, and the payoff maximal equilibrium would be the highest bid, obviously, because we're in a procurement auction, right? And interestingly, we find that quickly, very quickly. So the blue line is the result of NPGA. And as I was telling you, so we were quite interested in this scenario because you could think that maybe they only bid on the 50% share, but that would not be in equilibrium, because then there would be opportunities for one of the bidders to deviate. So they need to bid just aggressive enough on the 100% share as well. And here the gray range is again the range of allowable equilibrium strategies, and that's also what we find here. Right? The solid line is the winner-takes-all equilibrium, where they would only bid on the package, which is something they actually don't play, interestingly. So they really go for the payoff maximal one. Any questions here? If not, I would like to show you some more recent work, and please jump in if it takes too much time, but I think it's a good fit here. So after we've been working on this, and it's a paper that actually came out in August this year, we were thinking about how can we improve on this, and what is maybe an alternative. And this is joint work with Max Fichtl and Matthias Oberlechner here, who've done amazing work, I have to say. And this is now a different approach. And we were essentially thinking about how can we get around these neural networks, right? So you could think, oh, there is this neural network black magic. Maybe we can do this more directly. So in the technique that we developed, we always have 4-letter acronyms, as you see, is called SODA. So simultaneous online dual averaging. And the big difference to what you've seen before is that we don't learn pure Bayes Nash equilibrium. What we learn is distributional strategies. So these are the mixed extensions of pure Bayes Nash equilibrium. And they've been introduced by Milgram and Weber in 85. And SODA now operates on the discretized version of the continuous game. And we get away without these neural networks, as you will see. And what is the most important point is that these expected utilities are now linear in the distributional strategies. So the non-linearities in a way are soaked up by the strategies. Why is that important? Well, there is a theorem from a few years ago in a paper in math programming by Matikopoulos and Su, and they showed that they analyzed gradient dynamics for finite dimensional continuous action space games, complete information games. And they showed that if such games are pseudo-concave, and if the sequence of pure strategy profiles of gradient dynamics converges to a particular A star, say, then it is a Nash equilibrium. So per definition, our strategies are even linear in the distributional strategies, and whether they describe a pure strategy, that's something we can check, right? So essentially, if we converge, we now have evidence that it is also a Nash equilibrium. So let's step back. This was kind of a brief summary. This would be a pure Bayes Nash equilibrium, right? So you have different types, and your bid function gives you a particular bid AI here. A distributional strategy gives you a distribution over possible bids, right? And what we are working on is a discretized version of this, a discrete distribution of Bayes Nash equilibrium. So we discretize the type space here and the action space. And S here is now really this grid that gives us for each type and each bit a particular probability. This is in Rn times m. All right. So now you can write down the probability measure, so the joint probability, Si. And this just essentially is a formula that describes the grid that I was showing you previously. And we can formulate the expected utility, in this case, in a 2-player first price seal bid auction, right? So this means we only have 2 players, I and J. And we take the product of the utilities of a particular observation or type, nu I, playing a bit mu I against an opponent who plays b mu j, right? So we know that the utility for this, for these 2 bits, and if we know the type of bit I, and times the probability Si and Sj, right? So we essentially take the sum over all bidders' types and actions times the other bidders' types and actions. And now we can rearrange this into this formula here, or the shorthand, which you can see here. So Si, which is essentially our main variable, the probability of a particular bit type playing a particular bit, particular bidder type playing a particular bit, times Ci, which essentially soaks up all of this here. So the utility times the probability of the other player playing that specific combination. So what could you do with this? Well, first of all, if you were interested in computing a best response, it would be a simple linear program, right? S is now the variable, right? So you want to maximize S times Ci, which is, again, utility times the probabilities or strategies of the other. And we have a constraint, which essentially says, well, the sum of the probabilities of type nu I playing these different bits mu I needs to equal the marginal distribution, right? And we don't really need a best response, but you could implement a best response algorithm, for example. But what we implement is, again, a form of gradient ascent. It's not called gradient ascent here because we use a version that has better convergence properties and is actually much simpler to compute, which is called dual averaging. So, which is very much related to online mirror ascent for those of you who are in convex optimization. So the key difference, again, here, which you can see down here, it's the basic pseudocode is very similar to what you've seen before. So at each step, you go 1 notch in the direction of the utility gradient. And then instead of the projection, we use this specific formula, which has a specific regularizer, which has very nice properties that you can show, but that would certainly go too far here, right? So, but think of it as a version of gradient ascent that has nicer conversion properties. So how would this work? This first price seal bid auctions with 2 bidders. What you see on the left here, and here we assume a uniform prior, we randomly initialize this matrix. Right, so this is the colors here, or the gray shades are the probability or the SI, right? The probability of a particular type playing a particular bit, right? And originally this is randomly distributed here. And after, say, 300 rounds here, this is what we get, right? So the red line is what you would expect. You all know you play 1/2 of your evaluation in this game. So what you would get is essentially a discretized version thereof. So one of the questions that you can ask yourself is, does the epsilon-based Nash equilibrium of the discretized game that we play here approximate that of the continuous game? And that's what we essentially show in this paper. And this is a bit of ongoing work, but almost through. And it essentially says that the discretized version, if we have an epsilon-based Nash equilibrium for the discretized version, it's also, say, a kappa-based Nash equilibrium for the continuous game, right? So it's not too far away from the base Nash equilibrium of the continuous game. Yeah, so I can cut this short in the interest of time, but here are some empirical results again, and we compare NPGA and soda. You see that what we plot here is, again, L, our utility loss, which is in both cases super small again, but it's much faster, right? So while in NPGA we needed 15 minutes, here we need less than 2 minutes. I have to say, one has to be careful here. For example, also, these are symmetric games. If we have, and we go very deep in our paper that is currently being finished, but in general, Pseudo can also be very time consuming if you really go through all possible. So the discretization takes a toll, let me put it that way, right? So if you have a very large action and time space, then it can also be expensive. But for the games that we've looked at before, it's actually super fast, as you can see. And again, the blue marks here are what we find. This is again with asymmetries. And here we have evidence that what we find is indeed a Bayes Nash equilibrium, right? Even if we wouldn't know the analytical solution. So this is these are essentially two games we've taken from the literature where the asymmetric priors did have an overlap. This is the Plum example that I showed you before, and ones where we do not have overlap. This is again the LLG scenario that I've been showing you before with different types of payment functions, nearest zero, nearest VCG, and nearest bit. That's what these acronyms are all about. And I think the main takeaway again here is this could be solved in less than 3 minutes here with Soda. And it again took around 15 minutes with NPGA with uniform priors, right? And all that has to be taken with a grain of salt. If you have, very bad priors in the sense of, even a normal form, a normal distribution would probably take way more time.
Martin, have you looked at divisible good auctions at all? I think that would be a very interesting case.
Not yet. I think it should make things much faster if it's divisible, right? So because gradient is, that would be my expectation. But if you have a specific environment in mind, we would be super happy. We are actually currently looking into new environments to look into. Yeah.
Okay, so, because it's just a huge class of problems where like all commodity markets.
Absolutely.
Yeah, it's important. So let me think about it and I'll get back to you.
Super. Yeah, here, and I'm getting to an end here, right? So here, this is, again, the split award auction, and the picture looks pretty much like what you've seen with NPGA. So let me not spend too much time on this. Maybe a few words towards the end. So at first, remember, I was telling you computing these Bayes Nash equilibria in continuous type and action auction games. This is in a worst case view, which is what we typically do in computer science, in complexity analysis, super hard, right? And now I'm telling you, we have a simple gradient mechanism that always finds this, right? So this seems to be a bit of a contradiction here. And obviously we had to make some more assumptions, right? So we, for MPGA, we were talking about symmetric games, and that apparently gave the necessary structure to find actually Nash equilibria. But there are obviously also cases where gradient dynamics do not converge, right? So a simple game, just to give you a bit of an idea where the limits are, is a bilinear game that I've taken from a paper by Ledger, where you have two agents, and the first agent plays an action X, which is real or continuous, and the second agent plays Y. And the utility of the first agent is X times Y. The utility of the second agent is minus X times Y. And actually, the Nash equilibrium would be right in the middle, but the gradients, or if you look at the vector field, it orbits around the Nash equilibrium, right? So if, depending on, there are ways to get around this, but with standard gradient ascent, you might even diverge, right? So these are some cases where you cannot necessarily expect gradient dynamics to get to good results. Right, and there is more, but we are kind of scratching the surface on when does it work and when doesn't it. What we know is there are no possible game dynamics that lead to Nash equilibria in all games, right? So that is a given. And what we also know is that and that is very recent work in Europe's, that no regret learning and mixed Nash equilibria just don't mix apparently. So if you only have mixed Nash equilibria, very much like in here, or matching pennies type of games, then you often run into troubles, right? So that is maybe also interesting to understand. So brief summary, I was telling you about NPGA. This is a technique that learns pure epsilon Bayes Nash equilibria in auction games via neural networks and self-play. We approximate pure Bayes Nash equilibria, even in auctions with interdependent values, different types of priors and utility functions, which is, I think, interesting to for various purposes. And we can show that we converge in symmetric auction games. Empirically, we can do more, but we don't have a proof, right? Pseudo is an alternative. Here we learn distributional strategies. We don't need the neural networks and the evolutionary strategies. And we learn this in a discretized game. And whenever we find Nash equilibrium, or we find Nash equilibrium whenever we converge, right? So which is also nice because to check whether we converge is can be done very fast, as you have seen. So what is the essence of all this? I think there is some potential really for numerical methods, right? So when I talk to my peers here in the computer science department, many colleagues work on numerical methods for engineers, right? So they all solve super hard partial differential equations, and they've developed various types of techniques to solve these partial differential equations or do numerics. And I think there is room for this in economics as well, right? And I hope that's what we can accomplish. And by that, also push the boundaries of equilibrium analysis, which has been so restricting so far, right? If you think about arbitrary multi-object auctions, as I mentioned at the beginning, for very few environments, we really know the closed form solution. And it would be nice to at least get an approximation and see what would happen, right? And yeah, last but not least, if you're interested in that, one paper just came out in Nature Machine Intelligence. The other is in the making, but I'm happy to get your input. Thank you.
Okay, thank you very much. Does anyone has an immediate question at this point?
So why didn't you like the neural networks?
Why I didn't? Well, I have nothing against neural networks, but you've seen that computing these pseudo gradients is it's costly, right? And you're always in CS trying to speed up things, right? So and push the boundaries. An interesting question, by the way, is what can we say about computational complexity? Of these methods, and I think the short answer is it depends on the game, right? So in this paper by Kai and Papadimitriou, they've been exploring various types. They have a nice proof that approximating Bayes Nash equilibria is NP hard as well, right? But the type of game they look at has an exponential set of strategies. What we are doing is gradient descent, and if we have an exponential set of strategies as a player, we are exploring all of those, right? So, you know, we haven't found a trick to get around that, but in many games that we analyze, we don't have exponentially many strategies, right? So even in the combinatorial auctions I was talking about, you know, sometimes you assume single-mindedness, but rarely do you have exponentially many or explore those, right? So, yeah, this is maybe something to memorize. Yeah. And yeah, the training is a bit expensive, and also the analysis, right? So that's the advantage of Pseudo, since we don't know needs the neural network training. It's a bit easier to analyze as well.
So let me ask a provocative question, right? So what do I learn from this as an economist, right? Mm-hmm. So you just said that we can analyze auctions that we don't know equilibria of, right? Well, I get that, but if we need this to analyze this, then no bidders use it, right? So we analyze something that is vacuous in a sense, right?
A good question. So let me put it that way. I think this is very comforting in the sense we find this Nash equilibria with gradient descent, which is a very tractable algorithm, right? So say if you needed a very, very computationally intense algorithm to find Nash equilibria, how can you think that bidders would follow such a strategy if it's totally intractable? So that was kind of the question that I was asking at the beginning. So maybe from a theory point of view, and I think I hear you asking that question, I think it says, well, maybe Nash equilibria for many of these auction games are predictive because the type of computation that goes into finding the Nash equilibrium is not so hard after all, right? So it's gradient descent. I mean, what simpler algorithm can you imagine, right? So you don't need to study computer science to understand gradient descent. So every calculus student knows this. So that is actually quite nice. I would be much more concerned if there was no algorithm, even for standard games, to find this, because how can you believe that this fixed point that you have to compute somehow can be found by your bidders if it's apparently computationally so hard? So there is this famous quote by Kamalian saying that if your computer cannot solve it, how can the market, right? And I think that kind of nails it. So this is one insight. The other, I hope, contribution we can make in the future based on this is really exploring other environments, right? So, I mean, you're all very, very familiar with combinatorial auctions, and we've been struggling all along. I remember when the book that Peter edited in 2006 with Steinberg and Jörg Schorn, there was one commentary by actually Mike Ostrovsky, who pointed me to this, saying, well, everything in this book is just, or most of the work in this book focuses on the winner determination problem and so on and so forth, but we don't know the equilibrium strategies here, right? So we need to invent something here or find equilibria. And if you have numerical techniques, why not use them and get an idea what the equilibrium strategies would be? But I think that for me, the more philosophical insight is, well, maybe, so in general, and we are always talking about worst case in computer science, in general, finding Bayes-Nash equilibria in these continuous type and action games is super hard, right? So you cannot expect us to solve this, but for relevant classes of games, it might not be that hard. And I think this is maybe the main takeaway.
I mean, let me put it differently. I mean, that's a personal view. I never thought that Nash equilibrium is somehow predictive in auctions if it's an infrequent interaction, right? So how can we expect people to play Bayes-Nash from introspection? That doesn't make a lot of sense. But let me put it positively. Can I use your technique as a bidder, from a perspective as a bidder, to learn Nash equilibrium from frequent interaction? So suppose we have a bunch of very similar auctions. So suppose we don't have a common prior, and I just kind of observe the bids over time. Is there something from what you did that can be taken away, that I can use it to learn how to behave optimally? This ends up in a Nash equilibrium.
This is an interesting question from an economist who essentially challenges the fundamental solution concept here, right? So, I mean, yes, as we all know, Nash equilibria might not always be predictive, right? And we've all done lab experiments, right? So sometimes they are, and they can be helpful. We don't make a contribution on that one, right? So we just say, well, people are apparently interested in finding Bayes-Nash equilibria. They've been doing this for 60 years now. And it turned out to be, in general, super hard. And we essentially try to provide a technique that gives you an approximation, right? And whether this is predictive or not, well, I think this is a whole separate question, right? But if you challenge that, then you're challenging a lot of economic literature, I would suppose, right?
Yeah, why not?
Yeah, why not? Yeah, we should. So I think the repeated interaction is important. So let's just take one example real quickly. Wholesale electricity markets. You're participating, you're bidding every single day. There's tons of data in the United States anyway. We've got transparency of all the bids of all the players after a period, 90 days or 60 days, depending upon the market. So you've got tons of data. So you can take all that data, take your problem, you're not actually calculating Bayesian Nash equilibria. What you're doing is you're identifying what the residual demand curve is that you're facing, and then you bid the optimal supply curve in response to that. Mm-hmm. And you condition on the weather, you condition on everything you know, but and you may be using a neural net to figure out, or you might be using econometrics. I don't really care. But the point is that what you'd be doing would probably approximate some Bayesian Nash equilibrium, but you don't have to worry about it. You don't have to think about it that way. You're just, you're basically doing decision analysis. It's single person decision problem effectively. But that's fine, because that coincides with the Bayesian Nash equilibrium of this monster that you don't understand at all.
Yeah. Let me maybe add to that, and I want to get to Marian because I've been talking to her a while ago. So still we do Bayes Nash equilibria and try to understand kind of often weird equilibria that could exist or emerge, right? And in this local global model, Marian and Marissa back in 2013, they did, in my opinion, a very interesting study, right? So they looked at a version of this LLG model that is, a bit biased. So biased in the sense that one of the bidders is favored, right? So Marian, you might want to correct me if I'm saying anything stupid here, but this one bidder essentially gets his victory rent, and the other bidder not, right? And they found an environment with this biased version of the LLG model where the other bidder really overbids. So he bids, the local bidders are both actually only have valuations for one of the lots. Due to this bias in the mechanism, it turns out that one of the bidders, the one who is not favored, he overbids on the package, essentially in an attempt to drive up the price of the other and reduce his own payment, right? Marian, you let me know if this is a halfway decent summary. Interestingly, we could also model that. We had to massage or revise our neural networks in the sense that we don't only have one output, which would model single-mindedness, but we had outputs of these neural networks for item A, item B, and the package, right? And we essentially found also what Marian did. So why am I telling you this now after the discussion that we just had? I think this is an interesting way, kind of this type of equilibrium analysis and this type of comparative statics that you economists do all the time in a way, right? So we want to understand what changes if we add risk aversion. So are some impossibility theorems, Myers and Satterthwaite, still so bad if we add, look at different utility functions or different priors and things of that sort, right? And this should just be a tool that enables you to explore these comparative statics. And I think that's our aims have been way more humble than predicting the real outcome of a game, right? Really more as an exercise to do comparative statics. Right? So Marian, I hope I could answer also now your question that you asked me many months ago.
Yeah, thank you. So. Yeah, I guess, what we did was to allow multidimensional bits, and we used this special rule that favored one because it was the one with which we could analyze it. And I guess the effect would also appear with other rules.
Mm-hmm. Which is, I think, a super interesting insight, which tells you a lot about the stability of equilibrium and so on and so forth. And, single-mindedness being a very strong assumption, right? So I think this is super useful. And, Vitaly, you've been in enough spectrum auctions. So I think there are these types of comparative statics that you do in your head often, right? To explore different type of strategies. I don't want to go so far to say, well, this is the tool that every auction strategist should use, but what we experienced when we did lab experiments, we often thought now it would be super useful to have an equilibrium prediction with risk aversion, for example, or loss aversion, right? But it was, no way to get to such a prediction in short term, right? But it would be a nice baseline to compare against if you do analyze your lab experiments. And I think that was the basic driver here.
I mean, I fully agree. I mean, I framed it as a provocative question. Mm-hmm. I'm in a sense, I'm trying to push forward and seeing what can come beyond this, because the way I viewed your paper as I first stumbled upon this is, as I just told you before this whole presentation, is that we might be entering an age of artificial intelligence and computers essentially playing the games for us, right? be it auctions, be something else. And asymmetric information will not cease to exist, right? It will still be there, but we will have kind of super rational machines that will figure out strategies. And is this something that we can kind of use as a step toward this kind of, I don't know if it's proper termed, like training bit robots for spectrum auctions?
But maybe a much easier, and that goes back maybe to Peter's comment, a much easier environment is are games or auctions that are played much more frequently.
Yeah, absolutely.
And if you look at display auctions, this is a huge market, and there are so many of these games being played, and I think a myopic bidder that essentially just follows his gradient is maybe a much better prediction, or kind of a reasonable prediction, I would say, maybe to what is being done in practice. I'm not so sure if they always, have a quasi-linear utility function, at least to my knowledge. But you can model different utility functions. But what I'm saying is these are environments where, as you just say, you have these repeated auctions. There is a common prior because everybody observes the past history of bits. So you can at least estimate some common prior, hopefully, and maybe some of the assumptions that you typically make in equilibrium analysis are closer to reality than what they are in say spectrum auctions, where you play the game every 15 years or so, right? So from that end, maybe equilibrium analysis in general becomes more relevant in these environments. But again, this is not something we comment on in our paper. This is maybe above my pay grade here too. All right.
All right. So thank you very much. Does anyone else have a question? We already run way over time, but everyone who's still here seems to be interested, so we can spend more time if there is a question. If not, thank you again, Martin, for this very interesting, entertaining talk. And everyone else, we see you back hopefully in 2 weeks with Rakesh Vora.
Thank you from my side. Super interesting discussion, and I hope we can continue this. Bye-bye.